Hello all, today we'll discuss chapter 8, namely charge air motion within the cylinder. In this topic, we'll discuss the pattern of charge air motion for having a good combustion, less emission, and thus a good engine performance. This is the topic of this chapter. So at the beginning, we'll have a look on the intake generated flow, and then mean velocity and turbulent characteristic, and then swirl, tumble, squish. So this is a different type of the charged air motion pattern we usually have inside the engine, and then pre-chamber flow, and the last topic will be crevice flows and blowby. Gas motion within the cylinder is one of the major factors that control the combustion process in spark ignition engine, and then the fuel air mixing and combustion process in diesel engine. It has also a significant impact on the engine heat transfer. So you'll have a certain type of the charged air motion entering the cylinder that will control the bulk flow during the intake process, compression process, and thus continue to the expansion process. This bulk flow will determine the flame propagation. Some of this bulk flow will break into fluctuation flow, into turbulent flow, close to the compression, close to the end of the compression stroke, and this turbulent will enhance the combustion process. And then the bulk flow that is close to the wall will increase the heat transfer coefficient and thus increasing the engine heat transfer. And this one is not good from the engine performance perspective because you will have higher energy loss through the wall. So both the bulk gas motion and the turbulent characteristic of the flow are important. So the idea is to have the bulk flow. So sometimes it's called the organized flow if they are on the organized direction, and then break this bulk flow or organized flow into the turbulent at the end of the compression stroke. The initial in-cylinder flow pattern is set up by the intake process. So depending on the design of the intake system along with the intake port, we will have a different flow pattern inside the cylinder, and it may then be substantially modified during the compression. So we have a certain bulk flow pattern during the intake stroke, and then as the piston move up toward top dead center, some of this bulk flow might be converted into different flow pattern, and the ultimate goal is to have a high turbulence at the end of the compression stroke. So turbulence will enhance the combustion speed multiple times, that we need to have the turbulence as high as possible during the combustion process. Another important point here is to avoid excessive bulk flow around the spark plug to avoid overstretching of the spark, and thus misfire will happen. So the engine intake process governs many aspects of the flow within the cylinder. So it will generate different flow pattern, and then if we have a GDI, then we will have a different mixing process. So in this case, we need to design an intake system in such a way that this air motion will enhance the mixing process. In a 4-stroke cycle engines, the downward motion of the piston pull air into the cylinder. So this is clear because as the piston moves down toward bottom center, the chamber volume increases and thus the pressure decreases. And then as the pressure decreases and it is below the manifold pressure, then the fresh mixture enter the cylinder. So the intake flow velocity usually scaled with the piston speed, okay, and this is for the 4-stroke engines, okay. So as the engine is operated under high engine speed and thus higher piston speed, then the intake flow velocity increases. For much of the intake stroke, the annular gap between the intake valve head and valve seat is the minimum area for the flow. So, and we have talked about this one in chapter 6. So the gas velocity through this gap are the highest velocity set up during the intake process. So we have took a look on this one, and then looking at the possibility for the choking when the engine speed is at certain level. So if you'd like to review it again, it is in chapter 6. This feature is showing an example of a radial mean velocity VR and root mean square velocity fluctuation V prime R. So this is the feature on the left side at the valve exit plane. So this is the valve and this is the port, okay? And this is the radial, so it's mean the direction is on the vertical direction, okay? And then on the right side is showing the axial mean velocity. Axial mean velocity is mean the direction is in line with the cylinder axis, and this is the cylinder axis, this one, along with root mean square fluctuation V prime Z, and this is measured at 15 millimeters below the cylinder head, and this is at 36 after top dead center, and this is with the model engine operated at 200 RPM, and the valve lift is 6 millimeter, and the data for the velocity here is normalized by the mean piston speed. So when we formulate the velocity, we can write it down as the instantaneous velocity equal to the average velocity plus the fluctuation velocity. So if you look at the radial mean velocity feature on the left side, the velocity is maximum when it is in the middle. So this makes sense because the velocity at the wall, so either it is at this point at the valve seat or at the valve itself, equals to 0, and then it's generate a kind of parabolic feature here, and the maximum is somewhere here. And then this one is the fluctuation velocity, the line with the hollow dot here. And then on the right side is showing the velocity in the axial direction, so it is in this direction, so assuming that the flow is coming to this direction, okay. So the first one here is the axial velocity, and then the next one here is the root mean square fluctuating velocity. So this just showing an example of the calculated velocity at the minimum area there, and at this operating point 200 RPM, you can see here that the velocity, let's see here, so velocity here we don't see the okay, so this one is showing the scale. So you can imagine that the velocity can be about 10 times the mean piston speed, okay. Once again, it is at the minimum flow area, therefore the velocity is maximum. This picture is showing the sequence of Slitten photograph of intake jet as it developed during intake stroke. So Slitten Imaging, so in this case we put glasses on the cylinder liner so that we can capture the flow motion inside the cylinder. And in this photograph, it's shown at a different crank angle. So this is 30° after top center, and then 35 and so on. And you can see that this engine, I think, has one single valve, and it is at the center. So and this is the intake valve. Okay, and then you can see the flow pattern, although it's not so clear on this one. Okay, and then as the valve opens, so you will see a clearer flow pattern here. And this one, you see that high flow is entering the chamber and then hits the liner and then deflected to the center of the chamber. Okay, and this one is showing a large-scale rotating flow pattern within the cylinder by intake jet. So once again, here the engine has one intake, it is at the center. Okay, and then the flow pattern inside this chamber generate several rotating flow. So you can see here is the first one, so it's kind of rotating flow. So but it's not clear here whether this is clockwise or counterclockwise. We have a different flow pattern here, and you will see the next slide that this type of flow that has a axis of rotation perpendicular to the cylinder axis, it's called tumble flow. We'll have a cross tumble, and then we'll have a swirl flow as well. So we'll have a look in the next slide. And you can see also here another local rotating flow, and this one as well. So this rotating flow is a kind of organized flow, and this will need to be broken up into turbulent at the end of the compression stroke, because it is the turbulent that is used to enhance the combustion process. And from the ideal cycle analysis in chapter 5, I think, if we have a combustion under constant pressure, so it's mean the combustion duration is close to 0, then we have the best engine efficiency. So it's also happen in spark ignition engine, in diesel engine. If we can have a faster burn rate, then we'll have a better combustion performance. But as you might know, in spark ignition engine, this burn rate might be limited by the peak cylinder pressure and thus the knocking. In diesel engine case, it will be limited by the peak cylinder pressure and thus the material of the cylinder head, liner, piston, and so on. So if you have seen in the previous slide that the jet-like character of the four-stroke cycle flow interacting with the cylinder wall and moving piston creates a large-scale rotating flow pattern within the cylinder. So we have seen a localized rotating flow within the cylinder. Additionally, large-scale flow such as swirl and tumble. So swirl is a rotating flow with the axis in line with the cylinder axis, and then tumble is a rotating flow with the rotating axis perpendicular to the cylinder axis. So large-scale flows such as swirl and tumble can be deliberately set up through use of specific port and valve geometry. So we'll talk about this one in more detail later. So, and swirl is usually used in diesel engine to enhance the spray air mixing, and tumble is usually used in spark ignition engine to generate a high turbulent and thus a better combustion speed. So the detail of this large-scale flow are strongly dependent on the inlet port, valve, and cylinder head geometry. So we'll take a look on each of this component. And then this flow structure are thought to become unstable. So some of this organized flow will be break into the turbulent during later intake stroke and also during the compression process. And some of this will be dissipated at the wall, okay? And all of this will be converted into the thermal energy. However, the thermal energy is pretty small. It means that we won't be able to see the temperature increase due to this turbulent energy conversion. So such a rotating flow are usually sensitive to variation in the flow. So, and thus their breakup is likely to vary cycle by cycle. This is one of the source for cycle by cycle variation in engine. How about the flow pattern in two-stroke engine? The flow of air into the cylinder for the two-stroke engine differs markedly from the flow generated by the four-stroke cycle engine intake process. So I think we have studied this intake stroke and then scavenging process, exhaust stroke for this two-stroke engine in chapter 6. So the flow occurs while the piston is close to bottom center. And when the piston is close to bottom center, it means the piston speed is low. So it is the key part of the cylinder scavenging process and overlap the burning gas exhaust process. So we have the scavenging process, which consists of the exhaust stroke and intake stroke, and they occur simultaneously in two-stroke engine. So the entering airflow is driven through the transfer port near the bottom of the cylinder liner, so we know it, which open as the piston uncover derms, and this inflow is governed by the pressure difference, okay, by the pressure difference. Therefore, most of the two-stroke engine is equipped by a supercharging process. Either it uses a centrifugal compressor or blower or maybe crankcase supercharging. And this entering airflow is almost not pulled by the downward motion of the piston, okay? So the engine velocity generated in the air flowing into the two-stroke engine do not therefore scale with the engine speed. So it is scaled with this one, pressure difference, okay? And this happens for almost all two-stroke engine except for the two-stroke engine where air compression is achieved through use of a compressor or blower, and this compressor or blower is mechanically coupled to and driven by engine crankshaft. So it's mean if we have higher engine speed, we will have higher speed of the compressor blade, and thus we'll have also higher airflow. For this case, the airflow for this two-stroke engine is a function of the engine speed. Next one is the mean velocity and turbulent characteristic. As I mentioned to you in the previous slide, that the instantaneous velocity can be formulated as the average velocity plus the fluctuating velocity. And the second one here will govern the level of turbulence inside the cylinder. So the charge motion into and within the engine cylinder are turbulent. So it's mean we have a very high Reynolds number. And why do we need to have a turbulent flow? Once again, because we want to enhance the combustion process. And one of the parameters that enhance this combustion process is turbulence. So if we don't have a turbulence inside the engine cylinder, we won't have sufficient time for the combustion to complete at the end of the intake stroke. Once again, if we don't have turbulence, the combustion process won't complete at the end of the intake stroke. And this turbulence will enhance the combustion speed multiple times. So it can be twice, 3 times, 4 times, depending on the turbulent level set up in an engine. So for the turbulent flow, the rate of transfer and mixings are several times greater than rate due to molecular diffusion. And this molecular diffusion is the only process that make the transfer and mixing for the laminar flow. Okay, for the laminar flow, we only have molecular diffusion. So this turbulent diffusion results from the local fluctuation in the flow field. Okay, as I mentioned to you, this one is the parameter that will govern the level of the turbulence inside the engine. So this turbulent diffusion leads to increased rate of momentum, heat, mass transfer, and is essential to the satisfactory operation of spark ignition and diesel engine. Okay, so in diesel engine, the turbulent will enhance the mixing process and combustion. Okay, so if we have a good mixing process, it will ultimately also enhance the combustion process. So turbulent flow is always dissipative, so it's mean turbulent will dissipate quickly into the thermal energy. Therefore, when we design an intake system for a certain charge air motion is to have the airflow in such a way that we have a high turbulence close to the end of the compression stroke. Once again, because the turbulence is very dissipative, we don't want to have the turbulence during the intake stroke. Why? Because high turbulence during the intake stroke will dissipate quickly, and then at the end of the compression stroke, we might have a low turbulence. So what we want to have is to encapsulate, okay, to encapsulate some of the flow into organized flow. So in this case, we minimize the turbulent generation during the intake stroke, and then break this organized flow into turbulent close to the end of the compression stroke. So energy is required to generate turbulence, so it makes sense. So it's mean here we need to have something there to generate the turbulence. So either we have a squish pattern for the piston so that the swirl flow will be broken into the turbulence, and this will result in decent energy dissipation as well. So a common source of energy for turbulent velocity fluctuation is shear in the main flow. So this is another thing. So if you want to generate a turbulent for the thing that you learn in the fluid mechanics, you can have a jet flow. So jet flow always generate a high turbulence, but you will lose a lot of energy there. So turbulence is rotational and is characterized by a high fluctuating vorticity. So I think you learn about this vorticity in fluid mechanics. So this vorticity fluctuation can only persist if the velocity fluctuation are three-dimensional. So therefore, turbulence is always three-dimensional because it is generated by the velocity difference, which is dv over dx and dv over dy. That's why it's always three-dimensional. Let's take a look on the turbulent flow. The important characteristic of turbulent flow is irregular or random. Therefore, usually we use a statistical method to define such a turbulent flow. And the quantities, for example, like velocity under turbulent condition is usually represented as the mean velocity, and then the fluctuating velocity about the means, and several lengths and time scale. So in turbulent flow, we have a flow pattern with a different length scale and time scale. And in steady turbulent flow, the instantaneous local fluid velocity, U, is represented as the sum of the mean velocity plus the fluctuation velocity. And this is the formula to get the mean velocity. So this is the integration from t0 through a certain time interval, and then ut dt, and this is per 1 per time interval, and this is taken as the limit as the time approaching infinity. The fluctuating velocity component, so small u, is characterized by its root mean square value, and this is called turbulent intensity u prime. So U prime is one of the important parameter when we analyze a combustion process. And this U prime represent the level of turbulence. U prime is formulated by equation 8.3a. So this is a function of U. So U is the fluctuating velocity. And if we substitute U with the equation from the previous slide, where we know that U equal to U mean plus U. So if we substitute U with this one, you will get equation 8.3b. In engines, the application of this turbulent concept is complicated by the fact that the flow pattern within the cylinder changes during the engine cycle. So we will have different flow pattern during the intake stroke, during compression stroke, during the combustion. So we have a very high gas velocity because of the combustion. So in case of knocking, we might have a sonic flow there. So one approach used in quasi-periodic flows, such as that which occur in the engine, is ensemble averaging or phase averaging. So in this case, we average this velocity over multiple engine cycles. So usually velocity measurement is made over many engine cycles and over a range of crank angles. And the instantaneous velocity at specific crank angle position, so this V, in particular cycle, so cycle I here, can be written following this equation 8.4. So U as a function of the crank angle, theta here, and then comma I is the cycle number, equals to means of the velocity at this crank angle and cycle number plus the fluctuating velocity. The ensemble or phase average velocity is defined as the average of values at specific phase crank angle in the basic cycle. This feature is showing a schematic of velocity variation with crank angle. So the horizontal axis is the crank angle. In this case, it's written as time, which is crank angle as well, at fixed location in the cylinder during 2 consecutive engine cycles. So we have 2 chart here. On the top, it is for the case where we have low cycle to cycle variation. And then B here is when we have large cycle to cycle variation. Let's take a look on the upper feature here. So we don't see the dot line here as represent as the instantaneous velocity, because the dot line coincide exactly with the ensemble average. The ensemble average here is the average over a large number of such measurement, so large number of the engine cycle. So because of low cycle to cycle variation, the average of individual cycle coincide with the ensemble average. And then you can also see here, this is the instantaneous, so where you can see a very transient velocity, and then the average is smoother there. And then moving to picture B on the lower side, so we have the dot line here that represent individual cycle mean. Okay, individual cycle mean. Let's say this is cycle I, and then we have the other average, which is called ensemble average here. So once again, this is the average of many cycle, okay, of many cycle. And then there is a velocity that fluctuates about the dot line. So this is the instantaneous velocity for that corresponding cycle, which is, let's say, cycle I. So as you can see here, for the case that has a large cycle to cycle variation, there is a difference between the ensemble average from the individual cycle average. So when we talk about the smoothness of the engine operating condition, then this one has a better cycle-to-cycle variability. So it means it has less cycle-to-cycle variability. In turbulent flows, a number of length scales exist that characterize different aspects of the flow behavior. This feature is showing a schematic of jet created by the flow through the intake valve. So this is the intake valve, and this jet indicates the turbulent structure. So the largest eddies, or sometimes called the integral length scale, so in this feature is represented by Li. These largest length scale are limited in size by the system boundary. The system boundary can be this gap distance. It can be also the valve lift. And then we have also here the smallest length scale, which is represented by Lk. So K here stand for Kolmogorov. So Kolmogorov is the first scientist who proposed this theory. So the smallest length scale are limited by molecular diffusion. So it means that this Lk is controlled by the mixture viscosity. And then the third length scale here is called Lm. So this one is called Taylor length scale. And this Taylor length scale is also usually included to analyze the turbulent flows. For engine case, the ensemble average velocity is calculated following equation 8.5. So this is the ensemble average as a function of theta, which is the crank angle degree, equals to 1 over nc. So nc here is the number of cycles. So in the testing, we can use, let's say, 200 cycle or 300 cycle. And then this is the sum from I equal to 1 until nc u here as a function of theta, and then I here is the cycle number. And then the ensemble average fluctuation intensity can be calculated following equation 8.16. So the formula is similar to 8.5. In this case, we use the fluctuating velocity. This is the root mean square of the fluctuating velocity. This feature is showing an example of the ensemble average velocities throughout the engine cycle. And this is the engine data. So it is a motored 4-stroke, and the head type is L head. The engine speed is 300 RPM, and then the mean piston speed is 0.76 meter per second. And then it is shown here two velocity measurement at two different locations. One is location B here. It is close to the cylinder liner, and then C is at the center line. So this is the intake. So you will expect that the velocity measurement at B will be higher than the one at C, okay? And you can see it at the bottom here. So this one is the ensemble velocity measurement at point B. This is at point C. So you can see here that B velocity is higher than the velocity at C. This feature is showing the ensemble average root mean square fluctuating velocity, and also ensemble average individual cycle turbulent intensity as a function of crank angle. So the horizontal axis here is the engine crank angle, and then at two locations. So the location can be seen in the previous slide. Location B, which is this one, location B, which is near the cylinder liner, and this is location C at the center line. And you can see here that for location C, the fluctuating velocity has a decent difference from the turbulent intensity. And this feature is showing the ensemble average mean velocity. It is here featured on the left side, and it is normalized by the piston mean speed. and this is again a function of the engine crank angle. And then on the right side here is the u prime, so this is root mean square velocity fluctuation, also normalized by the piston speed, and both are at location B, okay, so it is close to the cylinder liner. So as you can see in here that the engine speed has a small impact to both of parameter of this velocity, which is mean and the fluctuating velocity. And this feature is showing the turbulent intensity as a function of the mean piston speed for a different flow configuration. So we have, for example, like 4S and then 2S. So this one is 4-stroke, this is 2-stroke, and this one is for the swirl port and then ported and so on. So as you can see in this figure that the turbulent intensity, so this is the parameter that is very important for combustion process, it is scaled linearly with the piston speed. So we can say that this turbulent intensity increases linearly with the mean piston speed.